Okay, we've introduced the concept of solving integrals or trying to solve integrals using integration by parts. We want to see how would we tackle this integral here, say the sine cubed of theta d theta. Now, like we talked about in our introduction video, when you're going to use this technique, you have to look at your integral and decide which part do I want to call u, so I can differentiate and get du, and the part that I call dv, I have to be able to integrate that to get v. That's one consideration. The other consideration is you want to choose your u and dv so that when you have the new integral of v times du, it's not going to be more complicated than the integral that you started off with. And again, the best way to get a feel for the technique is to just work through some examples. Now, with this problem here, again, the first question we should ask ourselves, can it be solved with the u-du substitution? And in this form, it doesn't look like it. But remember, sines and cosines are negative differentials of each other. So if we rewrote it like this, 1 minus the cosine squared of theta times the sine of theta d theta. Could we call this whole term here u? Well, if we do that, du would be equal to minus 2 times cosine of theta times the derivative of the cosine of theta, which is minus the sine of theta d theta. We call that u. This is du, and here we have a cosine of theta stuck in here, so that's not going to work. What if we just said let u equal to cosine of theta? Then du will be minus the sine of theta d theta. I'll put a minus sign here. So now the integral would become 1 minus u squared, and then just minus du, and that we can certainly integrate. So yes, it looks like this integral here certainly can be solved with the u-du substitution. But let's, for illustration purposes, let's try and solve it using integration by parts. And we'll keep it in this form then. So we have the integral of 1 minus the cosine squared of theta times the sine of theta d theta. And it's tempting, as you first tried up here, to call this whole expression here u. So if we do that, because then we have the sine of theta d theta, that we can certainly integrate. That's just minus the cosine of theta. So if we do that, it makes us think, at least at this stage of the game, that this integral here won't be any more complicated than the one we started with. But let's see. I'm going to say let u equal 1 minus cosine squared of theta. So du will equal, as we did before, plus 2 times the cosine of theta sine theta d theta. This is du, not dv. And then we have no choice. This has to be dv. So v is just minus the cosine of theta. Okay, so let's apply the formula. Here we'd have the integral, and this is the sine cubed of theta, equals u times v. So I have minus the cosine of theta times this, or I could say the cosine squared of theta minus 1 times the cosine of theta. Then we have minus the integral of v du. Here's v, here's du, with a minus 2 here, so we could make this plus 2. The integral of cosine squared theta times the sine of theta d theta. And it was our hope that this integral here would be less complicated than the one we started with. And let's see, if we call this, we don't call it u because we've already used that. Let's call this p, the cosine of theta. dp would be that, so it looks like this should be pretty straightforward to solve. Let p equal to cosine of theta. So minus dp will equal the sine of theta d theta. So this integral here is just now minus 2 the integral of p squared dp. That's p squared. The sine of theta d theta is minus dp, and we get a 2 here. So this would be minus 2/3 p cubed, which is this. So let's put all the pieces together, and we would have integral of the sine cubed of theta will equal this plus this, which is this. So we'll have the cosine multiplying through the cosine cubed of theta minus the cosine of theta minus 2/3 cosine cubed of theta. And this can just be written as 1/3 cosine cubed of theta. Do our subtraction there, plus an arbitrary constant. And that would be the solution to that integral there. So it was pretty straightforward. And again, it wouldn't even be the best technique to try to use on this integral. The u/du substitution works just fine, but we went ahead and did it just for illustration purposes of how to apply this integration by parts formula. So that's it for this problem then. Come back and join us for some more videos, and we'll try to solve some more complicated examples.